No problem. Anyways, come on. Yeah. Yes. So, Yashod, can you tell me that? So I'll go ahead and just
Yeah,
answer. Hmm. Yeah.
by looking in the graph, like e power minus x is
Yeah,
same similar to x.
that is true, but you can also do this Taylor X series expansion of e to the power x
Okay,
also, right?
okay.
That if you do that, then you will see, and so on. Okay, so in that limit, you see, because this x square will always be much smaller than x. Only by that logic, only I wrote that e to the power minus x is order of x. I'll show you one more thing. Let's look at it. Okay, just for the sake of curiosity, because it's interesting. Okay, e to the power x I wrote, right? See, they're tangents, right? You see how this will be a tangent. This is not a tangent, right? Up till now, you see this will become a tangent to x square. It should become a tangent to x square. Has it not become a tangent to x square? Sorry, this one. See, this has become a tangent to x square. See, in the limit xc, you see that
Yeah, yeah.
when I subtract, right? So it will become, and if I do this thing, it will become a tangent to x cube.
X cube.
See, see, it is a tangent to x cube. I go ahead and do x. You get it, and this is entirely from Taylor series expansion. Okay, this one I have to draw. See, that is the logic there. Okay, so this is the, because every time you do a increasing or if you include a higher order term, it will, you will start accounting for the next higher order term. Okay, okay, no problem. So now let's move on. There's this thing pending for a long time now. Any other questions?
Ah, no. I think I was having that doubt. It's I have some
Okay, so
idea right now.
this, so your answer got, your question got answered, right?
Yeah,
Okay, so now is 26th. What is it? August 2025. Let's quickly do that remaining part. So again, this is the course. We are in the, I think, what session is it? Hmm, I think it's sixth or something, fifth session.
sixth
Yeah,
session. Sixth week
sixth,
is
huh?
yeah, yeah.
Okay, but I think mine is the fifth only. Let me see. Let's check. I think we have completed four of them. This is the fifth one. Let's see. How many videos have I put? So today we'll just try to finish that finite element one. See, we have done four of them. This is the fifth session. Anyways, okay. So most of people watching this series would know me. We did some. We were looking at finite volume, finite difference, and finite element. The first lecture was about glimpse into numerical methods. The second session started with this idea. We discussed finite difference. The third session was on finite volume. The fourth session, we actually diverted, and we were actually discussing. We did a small revision or whatever, a recap of it, and then we went into the discussion of TDMA and how do you numerically do it, like how do you write the code about it. But now we go into the finite element part of it, and I had actually documented it properly. Let me also quickly start from, we can start from here, right? No. Session 4, how, where can we start from? Yeah. So this is the thing we were trying to solve for essentially, and now we'll look into the finite element methodology. just to contrast, because now is the correct time to contrast into things. These are the two schemes that we had looked at graphically. Again, not quickly going into what was the philosophy of finite difference and finite volume. Now let's look into the philosophy of finite element. Okay, what does finite element do? Okay, so first of all, finite element is one of is a if I, in my experience, what I was able to understand was that finite element is one of the first. It's unique in the sense that it uses functions rather than trying to get discrete values of the function the whatever function you have, some function that you will get analytically by some complex method, that uh, we finite volume and finite difference, both of them get the values at the at some nodes, right? In finite volume, you also get fluxes. So fluxes are gradient in that function. Okay. But finite element tries to construct that function. So it tries to give you, essentially, it can give you the functional value at any uh, at any what do you say, location from 0 to 1 or something. In your entire domain, you will have what do you say, you will have entire function, you for that matter, you will have a constructed function. But the problem with that function will be that it will not be accurate. And in principle, you would think that essentially, how does that help? It does not. It helps when you go into more complex problems. So when you go into a more complex geometry and scalability of the method, there obviously finite element um, prevails. But again, it depends on the problem also. So we see that for solid mechanics problems generally rely on finite element methods, whereas finite volume methods are used in heat transfer and fluid mechanics. So there is definitely on a on a fundamental philosophical level, you are not getting anything important. But so you're not getting very what do you say, uh, in comparison to finite volume as of now. Obviously, there are several advantages to it, finite element, but as of now, we don't see them now. Okay. Now, but essentially, the method is a very sophisticated way of figuring out the solution. That I must say. Okay, it's a very interesting way to look at it. And the way you do it is, earlier you had approximations of theta. So let's say there was some theta true, theta of n, which we wanted to approximate. Okay, theta of eta, and it satisfied this this governing equation and boundary condition. Let me also copy paste that. This one and this one, command cn, 1v, and this, let me remove this part. So these were the governing equations we had. We want to approximate theta. We do not have any other way to find out theta of x. Let me put theta of x. Okay. So what it says is that we will use a set of basis functions. Okay. We'll write it as AI phi, not phi, psi I. No, what is this? This is, let me write phi I only. That's not matter. It uses this function. Okay. Now this these are called basis functions. Okay. Basis functions. What are basis functions? Basis functions are those functions which, no matter what the governing equation is, what the boundary conditions are, we are going to construct the solution we want based on the governing equation, differential equation, using these basis functions. Okay, we'll talk more about what basis functions look like, how basis functions will look like, but essentially there will be some functions that we have, a set of functions that we have, and we will use them to construct our actual functions. Okay, you can think of it in that manner. There is also a test function. And now where does these terminologies are coming from? let's also understand that before going into what test functions are. But essentially, we will denote these test functions as like this. Okay, so test functions are this. I'll tell you what these test functions are, what these basis functions are. But before doing that, uh, first of all, let's understand one thing, that there are two important features of finite element there. It distinguishes from finite difference. I'll write that down. It distinguishes from finite difference in a manner that it seeks an integral solution. Seeks a weak solution, to be honest. It is based on a weaker. Let me put it as it is based on a weak formulation. Okay. Loosely speaking, like finite volume method. Okay. Let me just write this thing down and then tell you what do I mean by that. Okay. Okay. And I'll also write it it is different. It distinguishes from it distinguishes from finite volume in a manner that it seeks to uh, approximate the function itself rather than the functional values. In that regard, it is also different. In that regard, it is also different from finite difference approach. There are two guys. You guys are two there in the audience. Can you at least appreciate the second number, the second point? Well, not now, but at least can you appreciate that finite element, finite difference, and finite volume both were trying to approximate the functional values at discrete points. They were not trying to find the functions itself. Do
Yes,
you
sir.
agree at least that?
Yes, sir.
Okay. Now let me tell you what is this weak formulation and why finite volume also loosely speaking is a weak formulation method. Let me just quickly check also if we can call finite volume of weak formulation. Can we call finite volume method also a weak formulation method? Weak. Good question. Let's weak formulation of PD is obtained by multiplying by a test function and integrating over the domain. Okay. Integration by parts. Okay. Fine. That's okay. Okay. So maybe it's not exact, but I'll tell you what do I mean by weak formulation. Mm, good. Yes, FVM can be interpreted as a weak formulation, but in the literature it is more commonly described as conservative integral. Uh, can we not associate the weakness coming from integration? That's a very sharp observation. You're right. The weakness in a weak formulation comes primarily from the integration processes. Okay, let's break it down. Where does weakness come from? A PD in strong form usually requires solution to be sufficiently smooth. In weak form, we multiply by test function and integrate after integration by parts. So the weakness is not about using the integration per se, but how the integration by parts reduces the smoothness requirement of the solution. Does it also not, does it, is it also not, is it not also associated? Sorry guys, I'm like discussing this, but I'll make up for this discussion I'm having with ChatGPT associated with, because this is important. I don't think we get to get these insights from in a regular comparison of finite approximation methods. But anyways, let me just take 2 more minutes. Is it not also associated with, okay, wait, let me think. Okay, no, that's okay, that's fine. Okay, so if you were able to read what I was say, what it was meaning was that if you go ahead and increase this thing, integrate this thing, what you have here is e to the power x plus c, right? This is the integration, right? And you solve for c using the boundary conditions, right? That is something that you can do. And in that regard, actually, the weak formulation does not do anything. Okay, so maybe I'll remove this. I will remove this part. Okay, so what do I mean? See, what was finite difference method trying to do? Finite difference method, what did it do was, it was trying to uh, find the theta value at a node, essentially saying that the difference, it was trying to minimize the difference between the theta value, the actual theta value, and uh, the theta value, the true theta value at some node, right? That is something that was being done. Similarly, finite volume was also doing that. The word weak formulation is coming because it's coming from the fact that in finite difference there are certain candidate functions. In fact, the solution we get uh, will not satisfy, will not strictly specify this governing equation. So what do I mean by that? Actually, what do we do is, you tell me that this differential equation, the original differential equation, has a has a has a differentiability requirement, isn't it? What is the differentiability requirement? That it should be differentiable, right? But if we try to solve this equation, does our candidate function have to be double differentiable? Can a function which is just single differentiable be not enough,
Yes, sir.
right? Now, why does it matter? You will ask, like, how come this differentiability limit is coming into the picture? It is coming into the picture because theoretically, it does not matter to us from a applications point of view. If we're just trying to understand how the method works, we can go over it. But I'm trying to also emphasize on the keywords that you will always read or come across when you read about finite element methods. So they say that this is a weak, the finite element method seeks a weak formula, a weak solu weak seeks a weak formulation solution, or it is based on a weak formulation. Mm, okay, let me also write that. Does the weakness also not coming from the fact that we are not trying to, so just by reading my prompts also you'll get some idea, we're not trying to minimize error exact points, but generally around, but generally around a point in its neighborhood. Exactly, you're touching on another very important angle. In strong form, see, let's read this. A strong form formulation would be the PD must hold at every point in the domain. This is exactly what finite difference will do, right? It will try to, well, in finite difference, you're not trying to solve for every point, but at least in an exact sense, we are trying to emphasize that the PDE holds at every point. That means that you are requiring exact satisfaction of differential equations at infinitely many points, which is extremely strict. Okay, this is a very strict idea to have this, trying to figure out a theta which satisfies this equation at every point is actually a little stricter compared to when, if you integrate this thing in the weak formulation, the PD is only required to hold in an average sense. I'll discuss what do I mean by that. You forget about this tested against a family of weight functions in this thing. This means the residual error is not eliminated pointwise. Just let's read this. So the residual error is not eliminated pointwise. Okay. So we are not eliminating the error, or we are not minimizing the error at exact points, but in a region, in a neighborhood. Okay. That is what we are trying to do. Okay. So guys, from both, like amongst both of you, how much do you understand? Do you know about finite element? Is any one of you already familiar with what am I discussing right now? You already know of all these terminologies and the idea behind these.
Uh, so I know little bit about this terminologies, like basically that finite element methods.
But are you
So
aware of the discussion I'm trying to have here, or is
yeah,
it new
yeah,
to?
yeah, yeah. I'm able to catch what you're trying to describe or tell.
But you already knew it, or you're able to absorb it, or you already know it, this stuff.
No, basically, I know little bit of this stuff,
Okay.
concept
Okay.
of like like weak formulation and all
Okay.
in
Okay.
in regard of finite element. Yeah.
Okay. So again, I'll go back. The point was I was trying to get a sense of whether I was making some sense or not. So anyways, what we will do is, in finite difference, what we do is, rather than trying to satisfy the differential equation at certain exact points, what it does is it tries to minimize, uh, or it tries to satisfy the differential equation over a neighborhood. Okay, loosely speaking. And that is why it is a weak formulation, but because it is not exactly satisfying the PDE at a given point, but over a region. I'm saying that over a region, it is roughly the same. But at the exact point, I don't know. At the exact point, the error might be large. Error might be large. It might be some 5. But over other regions, it might be -5. So what that does is that the overall effect of this deviation from the true value cancels out. It might be high in certain parts of the neighborhood, but it can be also opposite of it in the other parts of the neighborhood. So essentially speaking, the overall effect over the neighborhood is small. So in that sense, we are actually allowing the approximate solution to deviate from the true solution, like largely, like it can deviate sufficiently high, like in principle, it can deviate largely from the true solution in certain point at certain points, but overall in a neighborhood the effect will be small. So you can think of it like that. We are trying to overfit over some data points. I have some points, but we overfit, right? We overfit, and that overfitting actually gives us a higher order. So you understand that, right? So what I'm trying to say is, suppose the solution is a straight line, but what we are trying to do here is, rather than allowing it to have this thing, we can also have this solution, which we know is a wrong solution. But essentially, this net error might be very small. It might be zero only. And in principle, finite element method allows that. Okay, that allows it. But essentially, when we go into deeper into how this finite element method works, we see that this error also will not be large. That error will also be small. So this weakness is just a temporary weakness. It will not be, it's not like it gives a wrong solution or something. Okay, it's a temporary weakness, only that the formulation is based on this idea of minimizing the error over a region rather than over a at a certain point. That is the first thing. Okay, so now if that is the philosophy of finite element methods, how do you minimize, or in principle, how do you minimize the error due to your approximate solution um, over a region? How do you do it? Any one of you can you tell me how do you minimize the error over a region? You might say
Maybe use some optimization method.
yes, we would need to do an optimization. But what function are you going to minimize if we are going to use optimization?
Like I watched lectures in this course only, the later part. So we can have error function like we do in regression and all.
Yes, so you say error function, right? But what will be the error function here? What will your error look like here?
Mm,
This one, this equation. Let's forget about this equation for time being. This one.
test function is there, right? Test function is like the no, no. Actually, I'm just trying to draw an analogy
Yeah.
between
Let
an
let me guide you that way. What if this is my error function? Whatever. What if I try to minimize this? What do you think? Will I, in some sense, be able to get the solution?
yes, we should.
In principle, we should, right?
Yes,
But my question is, again, as I said, I'm trying to minimize this error over a region rather than trying to minimize it at certain points. And there we start multiplying, we do a integration. So the next thing we do is we do a integration. Okay. So we are trying to minimize this integral. I'll call this as the integral for time being. Okay. And I'm not particular. Let me also. Can you tell me the limits of this integration? It will be this, right?
yes, sir.
Yeah. So this is essentially what we are going to essentially minimize. Okay, that is one thing. Now my question to you is, what stops? How will you stop this thing to happen? This stuff to happen? As I mentioned, this is a wrong solution. Definitely, this is a wrong solution. How do you stop this from happening?
When the difference becomes zero,
No,
means that
yeah. You were saying something. Yes, when the difference becomes zero.
the error becomes zero. Right? The
So suppose if I am saying this black line, with this black line, this integral will go to zero. I am saying that this will happen. Suppose
yes, sir.
I tell you this. What will your strategy be? What modification would you like to do in this integral so that this thing can be avoided? Can we avoid this integration by just quickly tweaking the integral a little bit? I'll tell you.
You mean
I'll
the
tell you. And
negative
this is
values? I mean, if the negative values are there, if we integrate, we'll add up. Those will get added up, and it will become zero. So what is the harm?
okay. No, can you tell me that again?
So like the deviation is right in is like in both directions, right? In some place
Right.
the function is going up, in some place it's going down. So if we are
Yes.
integrating, those things will add up, and eventually it will tend to zero or something in the ideal
Yeah.
case. So
Yeah. Huh. Yes, so you don't see a problem there, right? That is what you're saying. There's no problem.
Yes, sir.
Okay. So I'll try to emphasize of what I was trying to mean. Suppose this is my true solution. Then I'll mark my true solution, something like this. Okay. This is my true solution. I'll mark it. Mark it as green. Okay. And I also increase the width of it. Okay. Okay, again, one last thing. Whatever we are doing is the basics of it. So this is the Galkarin's method. I'm not going to discuss into details what finite element is. I also don't know also. This is the Galkarin's method that was discussed in that paper. That's the simplest finite element method. And that is essential for us to get a glimpse and understanding of what finite element is, how it is different from the other two methods. So that is what we're going to discuss. Coming back. Suppose this is my true solution, Purv. Okay, I'll write that down in green only. Okay. My question is if I simply start to minimize this integral I, if I do that, what stops my algorithm to not produce solutions like this? Solutions like this. Okay.
Absolute value, maybe. I mean,
Wait. Control V. Uh, just a second. I'll take your point. So this is a solution. We want something similar to what green line is. You said we want absolute values. Okay. So you're saying we'll do something of this sort. That's true. Okay. That is one way to do things. Is there
I
a
mean, the
simple, okay.
modulus. I meant modulus. The
Yeah,
absolute value.
modulus or square. That is okay. Let me do that. Okay. That is actually the most logical way to look at do this, right? That is the most logical way to look at it. But actually, that leads us to nowhere. That's the problem. That your state, like your suggestion was ultimate, like, is the best solution. The problem is, it does not help us a lot in deriving or at least in getting the theta. Anyway, we can't this problem becomes again a new problem which is not solvable for us, and at least not numerically. So I'll tell you what do we do. Like what is the philosophy of finite elements to figure it out. Okay, so what it does is it divides the algorithm, it divides the domain. Let me just quickly open that paper so that I can draw how do we. So again, before I do that, what do you think, Apurv, will happen if I start weighing the errors around certain points? Suppose I choose 3 points. Command C, Command V. There are 3 points, okay? Let's say this point. Let me put 4 points, okay? Let me put 4 points. What do you think a solution, let's not look at it this one anymore. Let's look at this one only. What do you think if I somehow enforce that the error near these 2 points or these 4 points should be zero? I want to enforce this. What will happen? Will the solution not look like something like this? Wait. If I would have chosen these points, the solution would look like this. You agree?
Yes, sir.
Now I'll remove this orange line and I'll tell you I increase the so the idea is that error near these points must be zero. I'm trying to enforce that. So what essentially what I will I can I do? What I can do is I can put uh I can put more weightage to errors near these points. Is that okay?
Sir, but what if the true solution is not known? So how do we know where to put the weight, the those points?
Not known, not known, not known. So you're looking at it a little like I've drawn it incorrectly. So the points that we will draw is actually not on the true solution, but on our domain only. So our domain, so it will be like this, no? So what I'll do is I know my domain. I'll put I'll put I'll put 4 points. Okay. You might say that, sir, whatever solution I told was easier. You will say that, and I don't see anything going like we can't end up to a good solution with whatever you are suggesting. And how will that lead to anything is unclear. But just for a few seconds, just believe me and let's see that if this can lead to something. Okay. My argument is that I know this is my domain. I chose certain number of points in my domain. I am saying, what if around these points, if I weigh the error around these points a little bit more than away from these points, my solution near these points is bound to be correct. What do you think about that? My optimization method should be able to give that, right? Do you agree? If I weigh something like this, the solution is bound to be like that. Again, the approximate solution has not changed, but at least around these points, the error is going to be zero. It will not be something like this. It will not be something like this. Uh, Let me draw that.
Variation will reduce, right?
So this will definitely not happen. Do you agree?
Yes, sir.
Why? Because we are giving more weightage around those points. Okay, that's okay, right?
Yes, sir.
Uh, okay. So now this weighing thing, how do we weigh? How do you weigh the error near some points? How do you do that?
Coefficients, like the weights are coefficients, right? You have to find the right
Not
coefficients.
coefficients. It's not coefficients. So essentially, what it's not the coefficients. We are saying uh, that what we are saying is, so suppose what are we saying here is it's not the coefficients that is there, which is important. Okay. So some theta is there. Okay. I'm plotting error now. Okay. I'm plotting error now. Let me plot error quickly. Okay. This is my error. And I have chosen my points to be like this. Let's say these are the points roughly. Now tell me if I'm doing an integral after all. So area under the integral is something that I'm calculating, right? I'll put that also up there. How do you how do you ensure that the error near these four, or at least the weight near these points is high? I'll suggest a way and you tell me if that is okay or not. What I'll do is I'll multiply it with a weighing function, weight of x. Okay, I'll put as v here. I'll put as v. Okay, what I'll say is how will my v look? Let me say my v looks like this. My V looks like this. Forgive me for this bad drawing. But you by now you must have gotten the idea. If my V looks something like this, do you agree that I'll get a good solution? Like at least at these points, my solution will be correct. What do you think? I'll try to shape fill it. Yeah. What do you think? If I multiply and this is my V of X, does this make any sense to you? If this is my V of X and this is my residual, I'll call this as residual, or I was calling it as residual of X. Let me write as res. Someone needs to answer. Will this be okay? If my V of X looks something like this, then at least I'll get this solution, this orange
Yeah.
solution.
Yes, sir.
And then I do that optimization. And if somehow I get a solution out of the problem has not changed, problem is still the same. You have to figure out how that theta has to come out and what optimization can we do. But at least in principle, if I do this, then I'll get a solution. This is the core idea behind finite element. What finite element does is, let me open that paper before I forget. Where is that paper? Oh, it's in that book. That's one. Yeah. So what it does is similar to the finite difference scheme only. It takes a certain number of nodes. Okay. Finite, this one takes a certain number of nodes. From a uh, from a this figure point of view, nothing changes. Okay. Nothing changes. Nodes remains the same. Okay. Nodes remains the same, but you start defining the elements. And now the element kind of stuff, how does an element look like? That now, obviously, that there has to be some elements there because it's a finite element method. So I'll tell you where does the element come in? Just bear with me for a few more minutes. This is the whole idea. Okay, this is the whole idea, trying to minimize the residue near a certain number of nodes. Okay. How do you define an element? What is an element? Element is the region. Well, element is a region between two nodes. Am I correct there? Yeah. Element
Yeah.
is a region between these two nodes. Okay, between these two nodes. And um, the idea is that around every node, this V of X will peak. It will be zero near away from the node, and it will so that error we don't care about that error. That error can be maximized. It can be a large error, but close to this point, the weightage should be high. So at least the function will not be will not deviate much near these node points. So this is the entire philosophy of finite element method. Okay, now let's come to the operational like details of the method. Or now we are going to get into the details. Okay, so this is a write-up I developed while preparing for the class. Yeah. So now, okay. So now remains this next step, this derivation. Let me do that derivation quickly up here. So how do we move forward from this one? This integration, this one. So what we do is, this is a convolution integral. Okay. This is called a convolution integral. We can expand it using integration by parts. That is one of the whatever we are doing now is an important prerequisite to finite element. Okay. So now, can anyone tell me the formula for finite difference? How do I write integration FG is? Is it something like integration? Nobody?
Fg minus f into integral g of g.
Is this okay or no? Is this
No,
okay?
f prime into integral g. I think it should be fine. F
Yeah.
prime into
So
integral g.
yeah, I'll put this also up. So f is integral f, and g is integral a. Do you anybody know how can I quickly see if this is right or wrong?
UV differentiation.
What the way I do it is just to check. I'll show it to you. Actually that integration by parts comes from this idea that u dash
UV.
v plus v dash u, and now just integrate the entire thing. So you get uv equals to u dash integration u dash v plus v dash integration v dash u, and now a little bit of manipulation so that you write u equals to uh, f and v equals to g. Oh, there's something incorrect there. This will not be integrated, I guess.
Fg,
Yeah.
small fg.
Yeah, it's a small word. Yes, FG. Yeah, you're right. See,
No,
that's
no,
why
it is
I made
small
a
g
mistake.
also
It's a small
in the
g.
topic.
Yeah, that's why I actually I generally like to derive this thing. So U have to be taken as U is what? I take U as capital F and G as small g. Then essentially I have is FG is what? Integral FG plus
Capital G.
integral.
I think the first term should be integral f capital G.
Just a second. Now V dash is F
No.
and G. No. What went wrong? V dash. So G dash and this
F.
F, right?
Capital F.
Yeah. So now if I take this one on that side, one here, this is okay, right? U is F dash, so F G, F G minus G dash F. So this should be G dash F, isn't it? The way I've taken it is incorrect, but it does not matter. G dash F. This is fine, right? It's, does anyone want to check if this is okay? I think this is fine because we just saw we can see it from here. Right? This one I think is bulletproof now. So you integrate the first one, do not integrate the second one, then you subtract, differentiate the first one, second one, and then keep on double integrate it. This should be capital F only. Wait, this should be capital F. Yeah, this should be capital F. This is okay. Okay, so now we'll do the same thing with this one. Recording, right? Let me just once check if we are recording or not. Yes, we are recording. Everything is okay. Yes. Now, if I want to do this, it has gone slow. Let me switch off my camera for time being. Now, I can be written as integration 0 to L v of x, and then also this entire thing. Integrate this also, right? Comes g theta by dx minus integral. I'll just quickly write e to the power x only for time being. And plus c also will come, isn't it? No, wait. So this thing plus c, isn't it? And minus integral 0 to L to subtract v dash. So I take a differential here, and this is what I write. So one point to note here is just look at how this step has actually made us go from d theta by dx, like double derivative to single derivative, right? Now what that does is it actually lifts a little differentiability constraint. Earlier, because of this integration effect, a more what do you say, less smoother function is also a candidate solution now, which was not true earlier. The candidate solution was because so that is something technically there. That is a technical detail, but that is why this weakness and stuff comes. Okay, so this is thing. This thing is there, and this will also be this will not be V by L. Wait, I made an error. Gross. What am I doing? Yeah, this should be this should be V. This should be V of L minus V of 0. I think this is okay. Guys must if if you see a mistake, please point that out. Huh? I'm also not doing it correctly sometimes. But yeah. Okay. Mm, yes. Now an important thing, because these are weights, right? Because already we have boundary conditions that satisfy that have to be satisfied, because we don't need explicit satisfaction or satisfying of, sorry, not satisfaction, satisfying of our governing equation at the boundaries. See, here we are lifting, similar to finite difference, we are lifting the um, satisfying of governing equation at the boundaries. We lift that. So because we don't need explicit satisfying of that governing equation there, we can say that we'll choose our v of L or a test function or a weighing function, which are 0 at x equals to at boundary nodes. So essentially, we'll ensure that the our test functions are 0 at the boundaries. Okay, we'll ensure that. And so that allows us to actually remove this entire stuff. We just remove this, right? We're just really interested into this second term. Let me just check if I have gone ahead and made a yeah, that's this one is fine. Okay, what else? We can go ahead and uh, yeah, this one is okay. This is, I'll write dv by dx. I think this one is okay. And then dx should also be there. Now what else? Acha, this plus c will not come because this is not a proper integral. This is an improper integral here at this point. Now we go ahead and split this integral to write. This one also I'll remove. Okay. Eventually we have this final expression is here. So certain manipulation is a prerequisite of finite volume method. That is something I wanted to emphasize. This manipulation is indeed an important characteristic of finite element method because we are not trying to figure out a function rather than points there. It's a little sophisticated. What else can we do? Can we move ahead and do anything else with this? Despite being weaker, this formation is significant. Okay, fine. Okay, so now at this point, we seek our numerical uh, approximation into the picture. Okay, now what do we do is something which I did not explicitly mention in the starting is, as I told you, we'll do this. Okay, we'll do this. In fact, actually, it has to be there. It has to be an summation there, which I didn't put properly, and this will be over I. So we assume. So as I told you in the early in the very early of our discussion, that theta we assume that it is a function of a lot of we start building it as a summation of a lot of basis function. Okay, this is what we do. And this basis function is our own choice. We choose whatever this basis function can be. This is our choice. Okay. It can be a piecewise function. So what we can assume is, suppose we can assume that this phi is a constant over this, these can be constants, or these can be these can be basis functions. Okay. And I'll tell you how these basis functions look like. Okay. One more thing. Let me just check if this is the final step before we go into numerics. Yeah, this is the final step. Okay. Okay. So now comes the trickier part. Okay. So now we have to first, now you see the problem has now a little bit gone more complex, more abstract in the sense that now we need to fix our phi's and also our v of x, our test function and basis function. Okay. This is something we need to fix. Now the problem has gone from a little difficult to very difficult. What is this? We're just complicating things. How are we going to get a solution out of this? The way to do it is first realizing that we have in a sense in this picture, if you see in a sense in this picture, if we look at this picture, what you will realize is we don't need to integrate it over the entire volume. We are actually only integrated over small volumes. You see, in a sense, these are these are not elements, but these are like these are not elements. We actually do need to integrate over only small volumes, first of all. Okay. And the first simplification that comes about here is in our identification of v of x. How does our v of x looks? Okay. How does our v of x look? Okay. V of x. Yeah, just give me a second. It's coming. So the next important stuff is, yeah. So let me just first substitute this thing, or let me first put a basis function. What can be a basis function? Let me ask ChatGPT, what is the simplest basis function in FEM? Yeah, this can be my basis function. Three simplistic piecewise constant functions. Right. So what we can have is the simplest one basis function could look like this. First of all, we divide our domain into some n number of nodes. Okay, n number of elements. So let me do that. So what we'll do is, so our element will look like something like this. Okay. Where do I copy this stuff? Yeah, just sounds okay. This is one element. Okay, I'll remove this. This is my one element. Across every two nodes, there is one element. And in this one, the function I will define is, this can be one way of doing things. It will be like some constant, some one. It can be one and this zero. The if x is less than, if x lies between some xi minus 1 and xi otherwise. Okay, you see, if I do this, okay, then what I have is, uh, and phi I is like, so for every element, there will be one shape function, one phi, right? So, what essentially we are saying is, in this framework, what we are saying is that our whatever function we are trying to make, we are saying that function value will remain constant between two nodes. That multiplies by AI. It gets multiplied by AI. AI fixes the value that it will have in this element. So are you guys with me at this point? You understand this, right? So
Yes.
you guys understand, right?
Yes, sir.
So this is clear. This can be one way. So essentially our problem will now, so you see, at this point there is a problem there with this formulation. This becomes a little problematic because either it will be zero, so our formulation will just quickly go. This term can go out. Okay, this term can just go out, and then we might not be able to get something. A better approximation. What is a better approximation? A better basis function could be a head function. I'll type it out. What a head function is. It will be a similar function again localized around a node or near a element. That so this one is called a head function. So what are we discussing? What we are discussing is a Galkarin's method. This is one of the first implementation of finite element method. That time it was not even called a finite element method. It was the Galkarin's method. And Galkarin came up with this hat function. I'll write that function down, or maybe I'll just copy paste it. There's a little change of notation, so let me just correct that too before we start discuss anything. Okay, now in contrast to how our this piecewise continuous function was looking like, how does this function look like? Let me draw that. And for that, I will also need another element to be there. Okay, and need two elements. So this function actually spans across two elements. Okay, I'll show you how it looks like. It looks like this. It is zero at uh, the edge at the endpoints of elements of the two elements, and it is one at the center point. This is our shape function. Okay. You might think why this, how do we get this thing there? You might ask, from where can we get this, what do you say, inspiration for arriving at this kind of hat function? Can someone tell me? Color. So I'll tell you what is the idea there. If you realize Gelkarin's method is actually a method which is characterized by stating that in this case, the shape function and the basis functions are the same. Let's go back to this picture. You see how this function, whatever I had drawn, is similar to this one, where the more weightage is given at the center of a node, at near a node, and the weightage is keeps decreasing down away from the node, right? So this is the head function. The problem, no, not the problem. Now, this head function comes from this idea. Maybe the inspiration came from the fact that if our shape function, if we can form our if we can form our theta just by a similar function of what we would use for our wing, that could be one inspiration of getting this shape function. Does anyone of you know why a shape function is rather very popular? It is also it also makes sense because it is the next best approximation. It is a linear approximation. Earlier we had this constant thing, right? This is linear in x. That is that is actually, we know it's a better approximation, right? Trapezoidal rule. We know trapezoidal is better. We know that between two nodes, the the functional value is supposed to change. So that makes sense, right? So with this idea, um, if I acha, okay, one more thing. Now, how do we implement this I? Suppose our theta is well defined. Theta is defined. What is our v of x? What is our v of x? Yes. Okay. So the way we do, we will approximate, or we will minimize this. We will say that this thing is zero is. We'll do it at a couple of points. We'll do it at every node. We have to do it at every node, right? We don't need to. Again, this problem will arise that if we do it over again, add across all points in one go. If we add across all points, then something can happen. Like error in this region can be um, positive, this region can be negative, it can flip, right? Right, that can also happen. So we don't want that. We want the integration over specific regions, specific nodes. So we have to solve for n number of nodes. Every node we have to solve this integral and get a zero out of it. You get this, what I said last, the latest thing I said? You get this point? So our v of x will have to be something of this sorts. Will be phi of j of x. And this I and j are different. So we actually have to solve I for different I and j's, where I and j will go from 0 to 1. This, are you able to understand how, why did I write this and this? Any questions or any reservations, any issues in digesting this? Are you able to digest it, or it's a problematic thing now? No comments? I guess it's not very clear. Yashod, you have a little more experience. Can you tell me if this is digestible or it is not digestible, the explanation I'm trying to give?
So, like this is fine, but exactly if I tell, like there is some background to this. Why, like there, like in Galeric, the method which you are explaining, Galerkin method. So there
Hmm.
it is considered that the shape function and the weight function are to be considered same.
Hmm.
So this is one like assumption kind of thing. So that is made. So the shape function which we are considering phi I of x, if
Hmm.
you are considering that as a linear function, then the
Hmm.
weight function which we will be considering will also be the same function. Like suppose if phi of x is in the form of ax plus b, then
Hmm.
our v of x will be also of the form ax plus b. So that is one
That's true.
assumption that is made in this formulation. Yeah, the description which you gave, it makes sense.
Hmm. But
Yeah,
Yashod,
like
I see it like this. So I am aware that there are other formulations also. This is not the only finite element method,
yeah,
right?
yeah,
And
yeah, yeah.
Gell-Curran methods is characterized by taking the finite the shape function and test function is identical. Is that also correct? So I
So
see it
this,
rather.
yeah, 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 please.
No, no, please go ahead. I'll complete that
So
later.
basically, this one, like the one which you are telling first, like I did not came across this word as test function for the first time. Like I'm hearing
What have you
basically.
heard? What word you have heard?
No, basically I heard about just about this basis functions, which are also
Okay.
called the shape functions. That is it is the reason because it describes the shape of the what we call our element. Suppose if
Achha,
you are
you have heard
considering
it.
the
You
element,
have heard weighing functions, right? Weighing functions is okay with you.
sorry,
Like you have not heard test function, but weighing,
yeah,
you
yeah,
understand
yeah,
weighing, right? Test function is essentially
yeah, wave
weighing.
functions.
It's for weighing.
Okay, okay,
Yes,
okay, 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 yeah, yeah, wave functions. Yeah, the one which I am talking, sir, please. In that reads Galerkin first in the first, like in
this
the
one.
top. Yeah, here
Yeah.
we, yeah,
Assume
yeah.
symmetric,
In that the
positive-definite,
assumption is
bilinear form.
asymmetric. Yeah. In that
Right.
method, we assume that the shape function and the weight functions are equal. So
So
we
what do they
formulate
say?
using that assumption.
Correct. Correct. But I would rather not like to call it as an assumption. Okay. Why do
Yeah,
I say this? Why do I say this? Why do I say that this is not an assumption? The reason being that at least in the way I have derived it, the simplest,
okay.
at least up till now, do you see a reason why we can't choose any v or any theta? At least with the explanations I have given. There might be other reasons also
Yeah,
which
correct.
you might know, but at least at this point of time, it's a choice. At least I am
Yes,
presenting it so. So in that
yes,
sense,
yes.
I feel that it's a choice. If you take
Yeah,
some other
correct.
choice, then it becomes a different
Your
formulation or
values
different
may
method.
change, like weight functions may change.
Yes.
Okay.
So with
Yeah.
this, again, my point was that this this I is connected with a node value. So I goes from 0 to n if you have taken n nodes, and j goes again. J again every time we are essentially minimizing or taking this integral value to go to zero at near a certain node. So this j represents that j value. So you will have to have n number of solutions to this integral. So you're every time you are making it zero at like around a different node. So you have to do it for n
No.
times around every node. So this j value is coming from there. That is the first thing. Okay. Now I see that we don't have much time. So we'll continue this next time. Probably next time we'll be finished with it very early. We won't need too much of discussion on this. Maybe half an hour, 45 minutes more. But anyways, let me quickly show to you what happens as we go ahead. So a little change of variables is there. But uh, if I if you excuse that, someone trying to join up. Okay, just give me a second. This one is also hanged. Okay, so this one, if you allow a little bit of change of notation, if I just start substituting these things, you will see two basically a set of equations with one summation over I, and there will be a set of equations. So J equations. Okay, J means every equation will have a index of J, whereas every equation will sum over I. Okay. And now because using this shape function, because we have now this is where the approximation and numerical method comes in. Okay, we have taken this shape function, and if I start substituting these things in there, essentially my problem will reduce to figuring out AI. Okay, I'll quickly show to you guys what the problem becomes. Problem becomes, let me, so I'll open this directly. Let's do this here only. So at this point, we just substitute everything in this integral that we were looking at. This substitution we have to do. Once we do this substitution, we get this delta theta by delta eta. Now the way we have looked at it is as Yashod discussed, linear. So either it will be 1 or -1, that derivative. Okay. Now with that, we'll discuss this in more detail next time. So this will be either 1 by delta eta or 1 minus 1 by delta eta. And so this integral gets simplified. This is why we were bound to do that integration, because we said that if we can approximate it with the basis function, we know that delta theta by delta eta is a constant. It is 1 or -1 depending on the region where you are integrating it. You can simplify that integral. That was the idea of FEM. And once we do that, we are left with this equation. Integral 0 to 1, this phi of this thing, entire thing, is this RHS is also there. So you get that also. Again, phi j is known. Phi j is known to us. This one, it's known to us. We can go ahead and substitute this one as well. Okay. If I do that, then I'll get further simplification, and I will get Ka by F. So essentially, this AI, there will be a set of J equations in so AIs, right? So there will be a set of AI values, and there will be so n unknowns and n equations you will get. And so essentially again going back to AX equals to B kind of format we will get. And using this AI values, we will go back, construct our theta using this, and figure out the solution. So this thing we have to do. So this a small part of it is left, and so we'll do that. Let me also quickly show the implementation to you guys before I close. The implementation I have done, we'll do it next time also properly, but I've done that, so let's do that. just see, and then we'll close because it is 8 o'clock already. Don't want to go into. Yeah. So this is finite difference only. No, this is finite element. So nothing much complicated. You're filling in this part of the code. You're filling in the values required. Uh, whatever this ax equals to b kind of thing happens. Then you solve for those ai values. Now you have to construct functions because now theta is not defined as points, a series of set of points. It is defined as a function. So you use AI values to define a function. Then you substitute theta. See, theta equals to AI times a function value, functional value. You see, so you construct theta as this, and you calculate theta at a certain set of points. And similarly, you will get this solution now. So this is the whole idea of finite element. Uh, I felt this much is enough in this course, this much introduction of finite element we can very satisfactorily move ahead of this finite approximation methods. We have spent a good amount of time on these. Uh, Definitely next class we'll also code this out so that nothing is remaining. We put the last nail in the coffin, finish it up. Nothing, no issues there. But I think this much is enough to the idea of finite element. And I guess you were able to appreciate that there is the difference between the three methods at this point of time. If you have any questions, we can discuss that.
So what is the advantage of finite element over finite volume?
Good question. Shivank also has a question. You can unmute yourself and ask if yeah. So something yes, as you mentioned, there are some advantages. Essentially, from what I have read, let me open that paper. That paper discusses that in good length. Maybe the next time we'll discuss that too. The advantage is essentially in the scalability of the method. So finite element can treat complex geometries and it is extendable to higher order accuracies also. It is easily accessible, whereas finite difference, it is it is easy to formulate. It's the easiest to formulate, straightforward. But it has a lot of complexities, like complex geometry is an issue. If you want higher order accuracy, that is an issue. And it also does not satisfy energy conservation and global local conservations. Then finite volume has a little bit tedious formulation. And so is true with the finite element also. That's the formulation is also tedious in finite element also, I feel. It says elegant formulation, but maybe it's an elegant formulation. I'm from a yeah, it can be an elegant. It is a scalable, definitely a scalable method. Uh, and this method too, finite volume is also difficult to extend to higher order accuracy. If your geometry is for complex geometry, then finite volume has certain issues in terms of accuracy. So finite volume is good in that sense. Okay. While it's global and local, both are yeah, that's true. So yeah, so these are the essential advantages and disadvantages of the theme. We'll discuss that too. I'll make sure that we discuss that too next time. Shivank, you have a question or you raised the you
Yeah,
raised hand by yeah,
yeah,
go ahead.
actually, okay. So I just want to ask, like, if you can help to in finite element, like, is through variational calculus. If you have any idea, then in the next class, if you can help.
What do you mean?
Actually, the finite element actually we deal in two ways. So the one which is more fundamental is through variational calculus. Do you have like if I'm not saying that it is not included in the course, but if you have some basic introductory idea, then you can
So we
include
did
in
this.
next.
So Shivank, we did this in today's lecture. So you can just go ahead and I'll upload the video. You can watch that.
Okay,
Okay.
you have okay, so I'm sorry, but you have started from variational calculus itself.
So what I have done is not focused into variational calculus as such. The definitely the way we do it is using variational calculus as you mentioned, but I tailor made it to specifically understand the philosophy of finite element, not going into variational calculus in any manner. But essentially, it does go into variational calculus, but I do not use that framework, at least in our explanations. You can go
Yeah,
ahead and watch the
just out.
lectures to figure it out.
Yeah, that's fine. I just want to know, like, if you have any expertise properly in this finite element. So I have actually certain doubts. So then I
In
will
finite
prefer for
element,
this. Yeah.
I don't have an expertise in finite element. No, I don't. So yeah, that's a short and straight answer. Yes.
Okay. I just asked because if it is possible, then I will ask in the next lecture. That's completely fine. I will restrict to the discussion related to these
No, that is
lectures.
okay. What maybe
Sir,
I
like I,
probably I won't be able to help.
sir,
Yeah.
like I just do Shivang's question, like for some guidance. Like there is this book of J.N. Reddy's, so Introduction to Finite Element. So I think that will be very helpful to you to understand this variational methods and all. I think so. You can refer to that textbook.
Oh, okay.
It's J.N.
Okay,
Reddy.
thanks. Yeah.
Yeah.
Generally, yeah.
Okay.
Okay, I will see, but actually I have gone through multiple lectures and I have some very basic stuff which is not getting cleared up. So just I took this privilege just to ask Shrey that if he had any expertise, then I can go ahead with the
That's
questions.
okay. Unfortunately, I don't work in finite element.
Yeah,
Sorry
it's
about
completely
that.
fine. It's completely fine.
Yeah,
So
that's
I
okay.
just asked. Thank you very much.
Yeah. So yes, guys. So you guys can start logging out. We'll end our class today. Okay.
Thank you.
Okay, sir. Thank you.
Thank you, everyone.